I have a beam. You'll see a lot of these when you start taking, or when you take solid mechanics course. Beams and beams and beams everywhere. Important structures. They are used to pretty much, a lot of structures we know around us can be simplified to a series of beams connected. Anyway, so in this case, we have this beam. Two forces are applied to it, right? 4 kilonewton there, and 8 kilonewton with an angle. And I also have a moment, like a moment couple, right? So this is the first force, this is the second force, and I also have a moment here applied in clockwise direction. Now, what I'm asked to do is to replace the force and couple moment, well, better to say the forces. I think there's a system at the end. Force and couple moment system. Yeah, that makes it work. System acting on the beam by an equivalent I forgot what to say. Let me see. By an equivalent resultant force, right? So we're asking to make it so simple that there is only one resultant force, and find where the line of action. That's a very ugly where. I was trying to write where here, so you can follow. Where the line of action of that force is. I'll put in parentheses from distance from point O. That's what I'm trying to find. Distance from point O, right here, point O. All right. So this is the second case, right? We have a couple of forces that are coplanar forces. They are not concurrent force. This is not a concurrent force system because they do not intersect in the same spot. So let's see how do we deal with this, right? We go about this the same way we were going about the typical system, right? We start with, as I said, we do it step by step. We go from, let me go back here, the second case, coplanar system. We go from the first one to the second one. So we find the resultant force and resultant moment about a specific point, this case, point O, for example. And then from there, you take the second step and make it more simple by just finding everything or simplifying the system to just a system with one resultant force. So I'll do the same thing here. The first step, we already know. We did it multiple times already. We have done it multiple times. We have a system of forces. We want to find the resultant force and resultant moment. Well, we did with resultant force multiple times. The resultant moment, I guess we went through an example or two, maybe. So let's start with resultant force about point O. All right, fine. Let's say FR about point O. Doesn't matter which point, right? Because it's FR, we can find it as long as we find it along the line of passing through point O. But let's go with FR about point O. We're finding the equivalent system at point O first and then make it more simple. So from before, I know FR is equal to summation of forces. This is a two-dimensional problem. So FR X and FRY. I just made it more, I don't need to put the vector here. Technically, they are not vectors. FRX and FRY, just two numbers. FRX would be summation of forces in X direction. FRY would be summation of forces in Y direction. Now, You tell me, what are the components of FRX? We have to find the components of this vector, force vector, 8 kilonewton. All right. So this can be decomposed to Fx and Fy. I'm going to call it F prime so it's not confused. We don't confuse that with what we have from before. To do that, what should I do? I know the value is 8 kilonewtons. I'm going to wait till someone speak up. 8 cosine, that was pretty advanced. You put everything together. Tan inverse 4/3. That is very true. So I'm going to go step by step, with your permission, Richard. So I'm going to call this alpha because I need to know this angle this force creates with the horizontal line to be able to find the components. So I'll find alpha first. Alpha is tan inverse, right? In this triangle, 3, 4, 5. 3, 4, 5. It's tan inverse 4/3. If you do this, you might even be able to. I can't finish that sentence. You might even know this angle by now. 53.13. We deal with this 3, 4, 5 ratio a lot. So alpha becomes 53.13, meaning that now Fx would be this 8 kilonewton times cosine, right, alpha. That's pretty much it. There is no other force in this system. Let's see if I can delete that. How about FRY? First, did anyone follow? Do you see where that FRX, where did that come from? Hopefully you did. If you didn't, stop me. FRY, how about FRY? What components do I have in Y direction? This is X direction. Don't get lost. This is Y direction. 8 sine minus 4. So does anyone else have any other opinion? So everyone agrees with Richard. Minus 4 sounds good. Okay, yeah. Okay. Minus 4 plus 8 sine alpha. Pretty much. That's the case. So minus 4, I have one force here. And then this 8 kilonewton there, right? It has a components in Y direction, which is upward. Maybe I should have put it here that I'm taking this as positive and this as positive. Goes without saying, considering where the coordinate system is. Plus 8 sine alpha. If I do the math, for the first one, you'll get 4.8. And for the second one, you'll get 2.4 kilonewton. All right. So far, so good. So pretty much this is what you have right now. You have a set of vectors, FRX, you know FRX, and FRY. And this is what you got. This is 0.0. This is 0.0. So this would be your FRX, this would be your FRY. In case you want to find the angle it creates, you want to find FR, right? FR is in this direction. Since you know both FRX and FRY, you can even find that angle. If I call this angle, let's say beta, beta would be, can someone tell me what beta is? Tan inverse of what? There is a reason I keep emphasizing this, because these are going to be used over and over, not in statics, everywhere you go. Dynamics, solid mechanics, machine design. FRY over FRX. Exactly. Thank you, Edward and Elizabeth. FRY over FRX. If you do this math, you will get, actually have to check my number because I can't do it in my head, obviously. 26, let's put it, 26.565. I don't know why did I go that far, but that's the angle. So now you know what FR is. You can totally identify FR, resultant force. Now let's take a look at resultant moment. Now, let's put it say now. Resultant moment about 0.0. Let's go like this. I'll put MR, and as always, I take, we know counterclockwise is positive. So that would be, we'll go back to what the general equation was. We said the resultant moment would be the moments created by or due to moving all the forces to the point we're finding a moment about. In this case, 4 kilonewton and 8 kilonewtons. So I'll put them under MI, I from 1 to 2. We have two moments, or we have two forces. Let's not put it 1 or 2. We'll just put it this way. Plus whatever free vector or moment couple moment we have. Let's just call this one M prime. That was a general idea, right? Moments that, because that M prime is just a free vector, can be moved wherever you want, doesn't matter if it's around that point or if it's around 0.0. But we are interested to also find the moments created by moving these forces to 0.0. So how do I do this? I did something very similar in last class, right? If you remember that example. I'll just write it M. Let's just write it directly. So I'm going to start with this force, 4 kilonewton. It is a distance D. So that would be 4 times distance D, which is 1.5. I'm moving it from where it is to 0.0. Positive or negative? Negative, positive, question mark. Oh, negative, positive. That's a question. Okay. I'm asking you, Voshan. So, positive. Okay, let's do this. Right hand rule. Right, my 4 fingers align the line of action, so the downward. Palm of my hand facing the point that I'm finding the moment about. Right? So that in that case is this way. I guess you guys see it the other way. Maybe I should do it this way. Right. And then, I don't know how you see it. I get confused if I do it that way. It's enough of just being in the positive x. Okay, yeah, it's negative. Right? Direction, palm of my hand, do it this way in 2-dimensional space. It's going to be clockwise. 3-dimensional space, going inside the screen. So that would be negative. Always use right hand rule. Things, it can be confusing. Yeah, no, it's all good. We all learn by making mistakes. Otherwise, nobody learns anything. Always, right. Okay, so 8 kilonewtons. Right? So let's go there. What do I do about that 8 kilonewton? It's in an angle. Right? So I have to find the distance, perpendicular distance from the line of action of that force on 0.0. Well, that would be a little bit challenging because if I continue this, this would be D. I don't know if it's that easy to find that D anyway, based on the geometry. So I'm going to use XY components, exactly. I'm going to use principle of moments. Right? The moment of a force about a point is the same as the moment of its components about a point. So I already decomposed it into fx prime, fx prime, and fy prime. All I need to know is that what distance should I apply them, multiply them with, right? So I'm going to write it this way. I'm going to write f prime y times something, f prime y x. So what did I do? Oh yeah, let's just start with x. Maybe it's better. It doesn't really matter, but leave some room. F prime x times something, and then leave some room. F prime y times something. Now, what are those numbers, somethings? What should I multiply f prime, fx prime with? 0.5, exactly, Richard, right? This is the distance f prime, fx prime has with, right? This is the line of action. If I continue it all the way here, the distance between line of action and point O here. So that's 0.5. Now, is it positive or negative? Negative. Right-hand rule, go this way, it's going to be clockwise, so it's going to be negative. Next one, how about fy prime? What is the distance for that one? Four and a half, exactly. Thank you, guys. Thank you for that. It gives me some confidence that you know what we're doing. 4.5, positive or negative? Oh, I suppose positive, exactly. So right-hand rule, follow that. Posi, as you say, correct. This way. So like clockwise, counterclockwise, so it's positive. So all you need to do is just replace these values. So that would be minus 4 times 1.5 minus a 8 cosine alpha times well, the distance, whether we put there, 0.5, and then plus 8 I lost it, fy prime would be a times sine alpha times 4.5. Now, are we done? Should I just sum them up and we're good? If we're good, we get resultant moment. M prime. Exactly, Elizabeth. Thank you. We forgot about that. We're missing that. Exactly. So I have to actually add it here. And that is going to be negative because it's clockwise. So I just add that minus 15. And this minus 15 there. So if my calculation is right, whatever comes out of it, the procedure is right. So whatever comes out of this, at least what I got, if this is the positive, oh, let's not put that positive. We didn't know what positive is. This would be 5.4, I believe, Newton meters. So now I have the resultant force, right, F, its components, based on its components, and MR. So now we are in step 2, right? Now we have a structure that we know FR and we know M for that. To find the distance from point O, that where the distance at which, if we move the resultant force, we can get rid of this R, kilonewton. Probably you are right, because everything is in kilonewton, exactly. The unit, at least you're right. Hopefully I did the right procedure. If someone does check this number, would be great. I think I got 5.4, and I guess it's kilonewton meter. Thank you, Samuel. This feels so good that I make mistakes and you figure it out. I'm proud. Not of myself, of you. I should be ashamed of myself, I guess. So structure, now we have an FR and we have the moment. Now I have to find the place that if I move the resultant force, I can get rid of the moment. To do that, pretty much I do what I explained before. So to find distance, let me go to next page and actually explain this better. I just want to make sure that you're all good. So far, here is what I have. Bring that back. So far, here is what I have. Right? I went from this to this. I guess I'm going to bring it back again. I went from that to this. So got rid of no force here, no moment here, nothing here. There, all I need right now is FR, if I got the direction right. And I got M as positive, so counterclockwise. M-O-R. Now the next step would that I want to go to next step where all I have, I'm just going to make it simple here, simplify it here. Well, let's use this color. There you go. All I have is just one FR. So I have to find out how far I have to move it. To do that, I'll say D is equal to M-O-R divided by FR, because I'm just finding the Y values are negative. Oh, my bad. It is not negative. It should be positive. The confusion comes from the fact that I made a mistake. I'm glad you mentioned that. This, I just put things there without paying attention to the direction, because FRX and FRY both are positive, right? So that, let me fix it. Yeah, not my day today, I guess. Thank you for mentioning that. That would be this way. That would be FRX and FRY. Hopefully that is not confusing anymore, Bobby, because the reason you were confused because it was wrong. That's FR and that would be beta. Better, right? Okay. Well, thank you. I was just going on. So now this should be fixed. This FR is also not in this direction. So this is FR. And then this is MOR. And eventually D, the distance from which this force has to be to make sure that we don't really have any moment and the whole system is simplified to just one force, just dividing the magnitudes. 5.4, we don't care about the directionality right now. So that would be 5.4 divided by 2, 5.4 divided by 2.4. I got 2.25, which sounds pretty right. So if I move this distance, the amount, I'll make somewhere there, let's say. I don't know how far it's going to be. Put the force somewhere here. I'm lost with colors. Somewhere, let's say here, distance D. So if this is it, just as long as the distance, perpendicular distance is correct, right? I don't know where it is going to be 2.25, but then that's just the whole system. So that's going to be the equivalent of the whole system. So I went from this whole mess of system of forces, and one is in angle, one is straight, the other, there is a couple moment, to just this structure with one force. Now, if you want to do analysis later on, again, in solid mechanics, anywhere else, machine design, it's much easier.